Welcome. Friends, I'm so glad you're here. Whether you're drifting towards sleep, unwinding after a long day, or simply looking for a quiet companion, you found the right place. Before we begin, I'd love to know, where in the world are you listening from? Perhaps you're wrapped in a blanket, sitting by a softly lit window, or resting somewhere under an open sky. Wherever you are, I hope you're warm, comfortable, and ready to wander with me into the vast reaches of interstellar space, where ancient wanderers carry messages from distant suns. If you find peace or curiosity in these gentle stories, please consider liking the video, subscribing to the channel, or sharing it with someone who might need a moment of stillness too. And to those who've already joined along, thank you. The object crosses Neptune's orbit on a Tuesday morning in October, though it carries no awareness of Earth's calendar or the small blue world that orbits closer to the yellow star. For 4.7 billion years, it has drifted through the space between stars, a wanderer roughly the size of a city block. Tumbling slowly through the cosmic void at 17 kilometers per second, its surface, darker than charcoal, bears the accumulated dust of interstellar medium, microscopic grains of silicon and carbon that settled onto its frozen bulk during the long journey between stellar neighborhoods. Each particle of dust represents a story spanning millions of years. Grains formed in the death throes of massive stars, in the cold molecular clouds where new suns are born, in the collisional debris of ancient stellar systems that ceased to exist when the galaxy was young. 3I/Atlas, the designation astronomers will assign in the coming weeks, follows a hyperbolic trajectory that speaks of origins far beyond the gravitational influence of our Sun. Unlike the elliptical paths of native comets and asteroids, this visitor's orbit opens outward like a cosmic slingshot, carrying it on a one-way passage through the inner solar system before flinging it back into the galactic dark. The mathematics of its approach encode the gravitational signature of its last stellar encounter, perhaps with a red dwarf star 37 light-years distant, where it received the final nudge that sent it tumbling toward our neighborhood of the Milky Way. The precision of orbital mechanics reveals that this encounter occurred roughly 2 million years ago, when early hominids were learning to craft stone tools on a world that the wanderer would not encounter for eons yet to come. Its composition tells stories of stellar nucleosynthesis in foreign suns, chemical processes that unfolded in stellar cores where temperatures reached 100 million degrees, and nuclear fusion forged elements heavier than hydrogen and helium. Spectroscopic analysis will reveal nitrogen compounds and carbon-based molecules forged in the atmospheres of giant stars that died before our own solar nebula began to condense. The object's interior, insulated by 4 billion years of vacuum, preserves chemical conditions from the epoch when the galaxy was half its current age and star formation proceeded at twice the modern rate. Each molecule locked within its icy matrix represents a sample from the interstellar medium of a younger cosmos, when the heavy elements necessary for rocky planets were still relatively scarce and the first generation of stars was still seeding space with the building blocks of future worlds. The visitor's surface temperature hovers at negative 250 degrees Celsius, a consequence of spending geological ages far from any stellar warmth. At this temperature, water becomes harder than granite. Carbon dioxide freezes into crystalline formations that would shatter like glass at the slightest vibration, and exotic ices form from compounds that exist only in the deepest cold of space. Yet even at these extremes, cosmic radiation slowly works its chemistry, breaking molecular bonds and creating new compounds that cannot form under earthly conditions. The Wanderer's outermost layers have been sculpted by 4 billion years of galactic cosmic rays, high-energy particles accelerated by supernova explosions and stellar winds from across the galaxy. The visitor's approach awakens detection algorithms in ground-based surveys designed to catalog potentially hazardous asteroids. Automated telescopes in Chile and Hawaii capture its movement against the stellar background, noting the peculiar trajectory that distinguishes interstellar objects from the countless pieces of debris left over from the solar system's formation. The Catalina Sky Survey, originally designed to track Earth-crossing asteroids, registers the object's motion as an anomaly worth investigating. Its brightness varies in a regular pattern as it tumbles end over end, each rotation revealing different surface features to the watching instruments. The period of rotation, roughly 8 hours, suggests a body that has been gravitationally relaxed over cosmic time, its spin gradually slowed by the subtle torques of passing stellar encounters. The discovery represents humanity's third confirmed detection of an interstellar visitor, following the mysterious acceleration of 1 Oumuamua in 2017 and the more conventional behavior of 2 I/Borisov 2 years later. Each detection has refined our understanding of how often such encounters occur and what they might reveal about the broader galactic environment. 1 Oumuamua's strange acceleration, possibly caused by outgassing of exotic ices as it approached the Sun, demonstrated that interstellar objects might behave in unexpected ways. 2 I/Borisov, more clearly recognizable as a comet with its developing tail and coma, showed that some visitors retain the pristine characteristics of objects formed around other stars. Now 3 I/Atlas promises to add another data point to humanity's growing census of galactic wanderers. Only now, with improved detection capabilities and dedicated sky surveys, does the astronomical community begin to grasp the frequency of such encounters. The Large Synoptic Survey Telescope, scheduled to begin operations in the coming years, will detect interstellar objects at a rate of perhaps dozens per year, transforming these cosmic messengers from rare curiosities into a regular stream of information about the galaxy beyond our solar system. Calculations suggest that at any given moment, several interstellar objects pass through the outer solar system, most too small or distant to register on current instruments. The galaxy, it seems, maintains a constant traffic of wandering worlds, each carrying samples and stories from stellar systems distributed across hundreds of light years. The wanderer's trajectory carries it past the orbit of Uranus, where it briefly interacts with the planet's complex magnetic field. The encounter, lasting only a few hours, creates subtle perturbations in both the visitor's path and Uranus's magnetosphere, a cosmic handshake between objects that formed under different stars. The planet's gravity provides a small but measurable deflection to the interstellar object's course, while the visitor's passage creates temporary ripples in the charged particle environment surrounding the ice giant. These interactions, detectable only by the most sensitive instruments, add precision to calculations of the object's mass and density. 3 I/Atlas becomes a messenger from this vast galactic ecosystem, a fragment of cosmic geology that has survived the journey between the stars to arrive, quite by accident, at the gravitational boundary of our own solar family. Its presence raises profound questions about the nature of planetary formation around other stars, the composition of stellar systems throughout the local group of galaxies, and the possibility that biological materials might survive the rigors of interstellar travel. Each measurement, each spectrum, each photograph adds to humanity's understanding of how matter moves through the galaxy and what stories it carries about the cosmos beyond our immediate stellar neighborhood. The mystery that accompanies this visitor lies not only in its chemical composition, but in the question of how many similar objects pass undetected through our solar system each year. Current estimates, based on the 3 confirmed detections, suggest that interstellar visitors outnumber long-period comets from the Oort cloud, making them a significant component of the material passing through the inner solar system. Yet their dark surfaces and small sizes make them nearly invisible until they approach close enough for detailed observation. The true population of galactic wanderers remains hidden in the statistical shadows of our detection capabilities. The irony settles quietly over the observational data. This visitor has traveled farther than any human artifact will reach for millennia. Yet, it drifts past our planet with the casual indifference of deep time. It knows nothing of the civilizations that track its passage, the instruments that measure its composition, or the questions it raises about the nature of interstellar exchange. It has witnessed the birth and death of stars, the formation of planetary systems, the collision of galaxies, and the slow evolution of the cosmos itself, all while maintaining the silence of absolute zero and the patience of geological ages. It simply continues its ancient trajectory, carrying its cargo of foreign chemistry toward an eventual exit beyond the heliopause, where it will resume its billion-year journey through the space between the stars, perhaps to encounter other solar systems in the distant future, other civilizations that might wonder at its passage and decode the stories written in its alien ice. The deep survey awakens in the pre-dawn darkness of the Atacama Desert, where automated telescopes begin their nightly scan of the southern sky. The Catalina Sky Survey has been monitoring near-Earth objects for decades, its algorithms designed to detect the subtle motion of asteroids and comets against the stellar background. But the detection of 3I/Atlas triggers protocols designed for a different kind of discovery. Within hours of the initial observation, alert networks ping observatories across 6 continents, each facility adjusting its scheduling algorithms to accommodate follow-up observations of the mysterious visitor. The object's hyperbolic trajectory immediately marks it as extraordinary, a wanderer from beyond the gravitational reach of our Sun, following a path that opens outward toward the infinite rather than closing into the elliptical orbits that characterize native solar system objects. The European Southern Observatory's Very Large Telescope Array repositions its 4 8-meter mirrors toward the coordinates transmitted from Arizona, each telescope controlled by computers that compensate for Earth's rotation and atmospheric distortions, with precision measured in milliarc seconds. In the controlled environment of Paranal Observatory, 2,400 meters above sea level in the Chilean Andes, adaptive optics systems sample atmospheric turbulence 500 times per second, adjusting deformable mirrors to counteract the blurring effects of thermal cells and wind shear. The resulting images reveal surface details on an object smaller than most asteroids, yet traveling faster than any comet from the Oort cloud, its dark surface reflecting less than 4% of incident sunlight, making it darker than fresh asphalt and nearly invisible against the cosmic background. Only its motion against the stellar field betrays its presence, a slow drift across the constellation Sculptor that speaks of vast distances traveled and gravitational encounters with stars whose names exist only in astronomical catalogs. The visitor's apparent magnitude varies between 21st and 22nd, requiring exposure times of several minutes, even with the largest ground-based telescopes. This faintness results not from extreme distance, but from the object's small size and remarkably low albedo. Characteristics that suggest a surface composition dominated by carbon-rich materials or organic compounds processed by billions of years of cosmic radiation exposure. The Hubble Space Telescope, orbiting 400 kilometers above Earth's atmosphere in a 96-minute cycle around the planet, receives priority target of opportunity scheduling to observe 3I/Atlas during its brief passage through the inner solar system, free from the distortions of weather and atmospheric scattering. Hubble's 2.4-meter mirror captures images with angular resolution limited only by the fundamental physics of light diffraction. Each exposure reveals new details about the wanderer's surface composition and rotation state, processed through spectrographs that separate reflected sunlight into its component wavelengths with precision sufficient to identify individual molecular absorption lines. The object appears elongated, perhaps 3 times longer than it is wide, tumbling in a complex rotation that suggests a history of collisions or tidal encounters during its journey through interstellar space. The rotation period, determined from the regular variation in brightness as different surface features catch and reflect sunlight, measures approximately 8 hours and 17 minutes, a value that has remained constant throughout the observational campaign, indicating a body in free rotation with no significant internal energy dissipation. This stability suggests either a monolithic structure or a rubble pile that has reached gravitational equilibrium over cosmic timescales. The visitor's spectrum shows absorption features consistent with organic compounds, carbon-based molecules that form naturally in the cold depths between stars, where molecular clouds provide the raw materials for complex chemistry at temperatures approaching absolute zero. Specific absorption lines indicate the presence of methane, carbon monoxide, and more complex hydrocarbons that could only have formed in the reducing environment of the interstellar medium, far from the oxidizing influence of stellar radiation. These compounds preserve chemical conditions from the epoch of the object's formation, potentially billions of years ago in a stellar system where planetary formation may have proceeded under very different conditions than in our own solar nebula. Ground-based radio telescopes joined the observation campaign, their massive dish antennas searching for any electromagnetic emissions that might indicate unusual activity as the visitor approaches the inner solar system. The Very Large Array in New Mexico, its 27 antennas arranged in a Y-shaped configuration across the desert landscape, detects faint radio signals at frequencies consistent with cosmic ray interactions on the object's surface. These signals result from high-energy particles, protons and atomic nuclei accelerated to near light speed by supernova explosions and stellar winds from across the galaxy, striking exposed ice and rock and generating electromagnetic pulses detectable across interplanetary distances. The radio emissions provide additional confirmation of the wanderer's composition and structure. The signal, strength, and frequency distribution match theoretical predictions for cosmic ray spallation in a mixture of water ice, carbon compounds, and silicate minerals, materials that tell stories of formation in a stellar system very different from our own. The presence of silicates suggests that the visitor formed in the inner regions of its parent system, where rocky materials could condense from the stellar nebula, while the abundance of ices indicates subsequent migration to colder regions or ejection into interstellar space, while volatile compounds remained frozen. The mystery deepens with each observation as accumulated data reveal characteristics that challenge existing models of interstellar object behavior, unlike 2I/Borisov, which developed a visible tail as solar heating sublimated its icy components. 3I/Atlas remains stubbornly inert, showing no signs of outgassing despite its approach toward the Sun and steadily increasing surface temperature. This behavior suggests either a composition dominated by more refractory materials, compounds that remain solid at higher temperatures, or a surface layer of accumulated interstellar dust that insulates the interior from solar radiation and prevents the sublimation that typically characterizes cometary activity. Thermal infrared observations from multiple space-based observatories, including the recently launched James Webb Space Telescope operating at the Earth-Sun L2 Lagrange point, measure surface temperatures that remain consistent with passive radiative equilibrium. The object absorbs solar energy at wavelengths corresponding to its distance from the Sun and re-emits that energy at longer infrared wavelengths without the additional heating that would accompany active sublimation of volatile materials. This thermal balance indicates a surface that responds to solar heating in a predictable manner, without the complex energy budget that characterizes active comets or asteroids with significant internal heat sources. The international coordination required for comprehensive observation reveals both the capabilities and limitations of Earth's astronomical infrastructure in the early 21st century. Major observatories schedule precious observation time around the visitor's predicted brightness and position. balancing the scientific value of interstellar object studies against ongoing surveys for potentially hazardous asteroids, exoplanet transit observations, and deep space imaging programs. The scheduling decisions reflect not only scientific priorities, but also the practical constraints of operating multi-million-dollar instruments with maintenance requirements, weather limitations, and the competing demands of international user communities. Smaller facilities contribute photometric measurements that help refine orbital calculations and monitor the visitor's brightness variations with time. University observatories, regional telescopes, and even sophisticated amateur installations add data points to the growing database of measurements. Their observations coordinated through online platforms that democratize participation in cutting-edge astronomical research. The collaborative effort transforms the solitary wanderer into a focus for global scientific cooperation, a reminder that cosmic phenomena transcend the boundaries drawn by human geography and political organization. Amateur astronomers, equipped with increasingly sophisticated CCD cameras and computerized telescopes available for a few $1,000s, contribute light curves and position measurements that would have required professional observatory resources just decades earlier. Their observations, processed through standardized photometric reduction software and submitted to international databases, provide temporal coverage that complements the intensive but intermittent observations from major facilities. The distributed nature of this observational network ensures continuous monitoring despite weather, equipment failures, or scheduling conflicts at individual sites. Orbital mechanics calculations, refined with each new position measurement, reveal the visitor's most recent stellar encounter occurred approximately 2 million years ago, when it passed within the gravitational influence of a red dwarf star designated Gliese 445 in stellar catalogs. The encounter, reconstructed through backward integration of the object's trajectory and the known motion of nearby stars, provided the precise velocity change that sent 3I/Atlas on its current trajectory toward our solar system, a cosmic billiard shot played out across interstellar distances with gravitational cues and stellar masses. Before that encounter, the object likely spent hundreds of millions of years drifting through the local interstellar medium, accumulating dust grains and experiencing the gradual chemical evolution that occurs in the deep cold between stars. The visitor's trajectory carries it past the orbits of the outer planets with clockwork precision, its path determined by the same gravitational laws that govern planetary motion and spacecraft navigation, yet operating on scales that dwarf human engineering experience. Unlike human-made probes, which carry instruments and communication systems powered by radioisotope thermoelectric generators or solar panels, 3I/Atlas remains silent, offering information only through the passive reflection of sunlight and the thermal radiation of its sun-warmed surface. It becomes a natural laboratory for studying interstellar conditions, a sample return mission executed by the galaxy itself over timescales that dwarf not only human civilization but the entire evolutionary history of complex life on Earth. Spectral whispers from afar emerge as Earth's most sensitive instruments dissect the faint sunlight reflected from 3I/Atlas, revealing chemical signatures that speak of stellar nurseries far beyond our solar neighborhood. The Wanderer's surface tells stories written in molecular absorption lines, each dark band in its spectrum corresponding to specific compounds that formed under conditions impossible within our Sun's gravitational domain. Infrared spectrographs aboard the James Webb Space Telescope detect the fingerprints of water ice mixed with carbon monoxide, methane, and more exotic molecules that crystallized in the frigid environment of interstellar space, where temperatures hover just a few degrees above absolute zero and stellar radiation remains too weak to drive complex photochemistry. The most remarkable discovery emerges from high-resolution spectroscopy conducted by the European Southern Observatory's Very Large Telescope Interferometer, where 4 separate 8-meter mirrors work in coordination to achieve the angular resolution of a telescope 40 meters across. The combined light reveals absorption features consistent with deuterated water, heavy water where one hydrogen atom has been replaced by its heavier isotope, deuterium. The deuterium to hydrogen ratio measured in 3I/Atlas differs significantly from the values found in solar system comets, suggesting formation in a stellar environment with different nuclear processing history. This isotopic signature provides direct evidence that the visitor originated around a star with different mass, age, and metallicity than our own Sun. Further analysis reveals the presence of formaldehyde, hydrogen cyanide, and complex organic molecules, including polycyclic aromatic hydrocarbons, carbon-based compounds that form naturally in the circumstellar disks around young stars and the photodissociation regions where stellar radiation interacts with molecular clouds. These compounds, preserved in their pristine state by 4 billion years of deep space refrigeration, offer a direct sample of the chemical inventory available during planetary formation in an alien stellar system. Each molecule represents a fossil record of stellar nucleosynthesis and disk chemistry operating under physical conditions that may have varied significantly from the environment that produced Earth and its neighboring worlds. The visitor's infrared emission spectrum, captured during its closest approach to the Sun, reveals thermal characteristics that challenge conventional models of small body composition. As solar heating warms the object's surface from negative 250 degrees Celsius to merely negative 100 degrees, certain spectral features strengthen while others fade, indicating complex phase transitions and chemical reactions occurring in real time. The thermal response suggests a layered structure with different compositions at varying depths, perhaps indicating multiple episodes of material accretion during the object's interstellar journey or heterogeneous formation conditions in its parent protoplanetary disk. Polarimetric observations, measurements of how reflected sunlight becomes polarized upon scattering from the visitor's surface, provide additional clues about its physical structure and composition. The degree and angle of polarization vary systematically with the object's rotation phase, indicating surface regions with different grain sizes, compositions, and optical properties. These variations paint a picture of a world with a complex geological history, despite its small size and presumed lack of internal geological activity. The polarization characteristics most closely match those of carbonaceous chondrite meteorites, the most primitive materials found in our solar system, suggesting that 3I/Atlas preserves chemical and physical conditions from the earliest epoch of planetary formation. The mystery of the visitor's composition deepens when spectroscopic observations reveal absorption features that cannot be definitively identified with known molecular species. Several weak absorption lines in the near-infrared spectrum remain unassigned despite comparison with extensive laboratory databases of molecular spectra measured at low temperatures. These unknown features may represent exotic molecular configurations that form only in the unique environment of interstellar space, where cosmic radiation, magnetic fields, and the almost perfect vacuum create conditions impossible to replicate in terrestrial laboratories. Radio observations conducted by the Atacama Large Millimeter Array detect molecular emission lines from trace amounts of carbon monoxide and methanol sublimating from the visitor's surface as it approaches perihelion. The line profiles, the precise frequencies and intensities at which these molecules emit radiation, reveal information about temperature, pressure, and molecular motion within the thin atmosphere that surrounds 3I/Atlas as solar heating drives sublimation of surface ices. The detection of molecular emission confirms that the visitor retains volatile materials despite its billions of years in interstellar space, where cosmic radiation and micrometeorite bombardment gradually erode exposed surfaces. The spatial distribution of these molecular emissions, mapped using interferometric techniques that combine signals from multiple radio telescopes, shows that outgassing occurs preferentially from regions of the visitor's surface that face the Sun during its rotation period. This asymmetric activity pattern suggests either compositional variations across the surface or differences in thermal conductivity that focus sublimation in specific areas. The resulting weak coma, a tenuous atmosphere of gas and dust surrounding the nucleus, remains invisible to optical telescopes but registers clearly in radio observations sensitive to molecular transitions. Detailed analysis of the molecular line profiles reveals Doppler shifts that provide independent confirmation of the visitor's rotation period and axis orientation, as different portions of the spinning object move toward and away from Earth. The emitted radiation experiences frequency shifts that encode information about the three-dimensional motion and structure of the outgassing regions. These measurements complement optical light curves and provide a complete picture of the visitor's orientation and rotation state as it tumbles through the inner solar system. The chemical inventory detected in 3I/Atlas includes several molecules of particular astrobiological interest. The presence of hydrogen cyanide and formaldehyde, both important precursors to more complex organic chemistry, raises questions about the potential for interstellar objects to transport biologically relevant materials between stellar systems. While the extreme cold and radiation environment of interstellar space would prevent biological activity as we understand it, these molecules could serve as starting materials for prebiotic chemistry if delivered to environments with liquid water and energy sources. Laboratory experiments conducted in parallel with the observational campaign demonstrate that the molecular combinations detected in 3I/Atlas can indeed form through purely chemical processes in simulated interstellar environments. High-energy particle bombardment of ice mixtures at liquid nitrogen temperatures produces many of the same compounds observed in the visitor's spectrum, confirming that complex organic chemistry can proceed without biological involvement under the conditions that prevail between the stars. These results support scenarios in which interstellar objects serve as chemical reactors, slowly processing simple molecules into more complex forms during their eons-long journeys through galactic space. The isotopic ratios measured in various molecular species provide additional constraints on the visitor's formation environment and subsequent evolution. The ratio of carbon, 12 to carbon-13 in carbon monoxide, differs from solar system values, indicating nucleosynthesis in a stellar environment with different initial composition or evolutionary history. Similarly, the nitrogen isotope ratio measured in hydrogen cyanide suggests formation in a molecular cloud enriched by material from massive stars that underwent different patterns of nuclear burning than the progenitors of our local stellar neighborhood. Spectroscopic observations continue throughout the visitor's passage, creating a time-lapse record of how its chemical signature evolves as increasing solar radiation drives physical and chemical changes on its surface. The gradual appearance of new absorption features and the strengthening of existing ones document the progressive sublimation of surface layers and the exposure of materials that have remained frozen since the object's formation. Each spectrum becomes a snapshot in the visitor's geological awakening as it experiences the first significant heating in billions of years. The accumulated spectroscopic data transforms 3I/Atlas from an astronomical curiosity into a comprehensive case study of interstellar chemistry and planetary formation processes operating under conditions that differ substantially from those that shaped our own solar system. Every absorption line, every isotopic ratio, every molecular detection adds to humanity's understanding of how matter behaves and evolves in the space between stars, where the building blocks of future worlds drift in the cosmic dark, awaiting their next gravitational encounter with the light and warmth of stellar systems. Gravitational archaeology begins with the mathematics of celestial mechanics. As astronomers trace 3I/Atlas backward through galactic time, using the same equations that govern planetary motion and spacecraft trajectories, The visitor's current trajectory, precisely measured by weeks of astrometric observations, encodes a complete record of its gravitational encounters with massive objects over the past several million years. Each stellar passage, each near miss with a planetary system, each drift through the galactic disk has left its signature in the object's velocity vector and angular momentum, creating a navigational record written in the language of orbital dynamics and readable by those who understand the gravitational choreography of the Milky Way. The process of trajectory reconstruction requires supercomputer simulations that model the motion of thousands of stars within the local galactic neighborhood, accounting for their gravitational influences on small objects like 3Y/Atlas as they migrate through interstellar space. The European Space Agency's Gaia mission, which has measured the precise positions and motions of over 1 billion stars, provides the stellar census necessary for these calculations. Each star's mass, velocity, and orbital characteristics contribute to the complex gravitational field that has shaped the visitor's journey, creating a three-dimensional map of gravitational influences spanning hundreds of light years and millions of years. Working backward from the object's present position and velocity, the simulation algorithms integrate its trajectory through the evolving galactic gravitational field, accounting for the slow rotation of the galaxy itself and the orbital motions of individual stars around the galactic center. The calculations reveal that 3I/Atlas passed within the gravitational sphere of influence of the red dwarf star Gliese 445 approximately 1.97 million years ago, receiving a velocity change of roughly 3 kilometers per second that redirected its path toward our solar system. Before that encounter, the object followed a significantly different trajectory that intersected with the gravitational neighborhoods of other stellar systems, each contributing smaller perturbations to its interstellar wandering. The red dwarf encounter represents a crucial moment in the visitor's billion-year journey, transforming it from a random wanderer in the local interstellar medium into a directed projectile aimed at our solar neighborhood. Gliese 445, a star roughly 1/10 the mass of our Sun and located 37 light-years from Earth, provided exactly the right gravitational deflection to send 3I/Atlas on its current hyperbolic trajectory. The precision of this cosmic billiard shot becomes apparent when simulation parameters are varied slightly. Changes of just a few hundred kilometers in the closest approach distance to Gliese 445 would have sent the visitor toward entirely different regions of the galaxy, making its detection by Earth-based astronomers impossible. Further archaeological reconstruction reveals the visitor's deeper history, tracing its path back through multiple stellar encounters over the past 10 million years. Each gravitational interaction modified its trajectory incrementally, creating a complex orbital evolution that resembles a three-dimensional random walk through the local galactic neighborhood. The object appears to have spent most of its interstellar journey moving slowly through the sparse material between star systems, occasionally receiving gravitational kicks that altered its direction and velocity when passing near massive objects. The mystery deepens when the trajectory reconstruction extends beyond 10 million years, approaching the computational limits of current galactic models and stellar position data. The uncertainties in stellar motions and masses accumulate over these longer timescales, creating multiple possible histories for the visitor's origin. Some scenarios suggest ejection from a planetary system within 50 light-years of Earth, while others indicate a more distant origin requiring hundreds of millions of years of interstellar travel. The mathematics of chaos theory apply to these calculations. Small uncertainties in initial conditions amplify exponentially over time, making it impossible to determine the visitor's precise birthplace with current observational capabilities. Spectroscopic analysis provides independent constraints on the visitor's age and formation environment, complementing the dynamical reconstruction with chemical evidence of its stellar origins. The isotopic ratios measured in various molecular species indicate formation in a stellar system with slightly higher metallicity than our Sun, a star enriched with heavy elements from previous generations of stellar nucleosynthesis. This chemical signature suggests origin in a stellar system younger than our own, formed when the galactic disk contained a higher abundance of elements heavier than hydrogen and helium. The object's physical characteristics also encode information about its formation and subsequent evolution. Its elongated shape and complex rotation state suggest either a violent ejection event that imparted significant angular momentum or subsequent collisional modification during its interstellar journey. Theoretical models of planetary system formation predict that objects ejected by gravitational interactions with giant planets should retain certain dynamical signatures that distinguish them from materials ejected by stellar encounters or disrupted by tidal forces near their parent star. Comparison with the orbital characteristics of long-period comets from our own Oort cloud reveals subtle differences that highlight the alien nature of 3I/Atlas. Solar system comets typically approach on nearly parabolic orbits that barely exceed the escape velocity, having been perturbed from their distant orbits by stellar passages or galactic tides. The interstellar visitor, by contrast, arrives with excess velocity that speaks of acceleration in foreign gravitational fields and ejection from stellar systems with different architectures than our own. The gravitational archaeology extends beyond individual stellar encounters to consider the visitor's motion through larger-scale galactic structures. During its multi-million-year journey, 3I/Atlas has traversed spiral arms, crossed through molecular clouds, and experienced the varying gravitational fields associated with different galactic environments. Each region contributes its own signature to the object's dynamical evolution, creating a complex interplay between local stellar encounters and global galactic dynamics. Recent advances in computational astrophysics allow astronomers to model these large-scale influences with unprecedented precision, incorporating the effects of dark matter substructure, galactic magnetic fields, and the collective gravitational influence of stellar clusters and associations. The simulations reveal that interstellar objects like 3I/Atlas serve as natural traces of galactic structure and evolution, their trajectories encoding information about the distribution of matter throughout the local galactic neighborhood. The archaeological reconstruction also provides insights into the frequency and characteristics of planetary system disruption events that eject material into interstellar space. The discovery of multiple interstellar objects within a few years suggests that such ejections occur regularly throughout the galaxy, creating a constant population of wandering worlds that migrate between stellar systems. Each visitor represents a sample from this vast galactic ecosystem, carrying chemical and dynamical information about planetary formation processes operating under diverse stellar conditions. Statistical analysis of the growing population of known interstellar objects reveals patterns that constrain models of planetary system architecture and evolution. The size distribution, velocity dispersion, and chemical characteristics of these visitors provide direct observational evidence of how planetary systems form, evolve, and occasionally disintegrate under the influence of stellar companions, migrating planets, and external gravitational perturbations. The gravitational archaeology of 3I/Atlas thus extends far beyond the reconstruction of a single object's trajectory, becoming a window into the broader processes that shape planetary systems throughout the galaxy. Each calculated position, each gravitational encounter, each stellar passage adds to our understanding of how matter moves through the cosmic web of gravitational influences that connects all stellar systems within our galactic neighborhood. The irony of this archaeological endeavors lies in its fundamental limitations. The very gravitational processes that make trajectory reconstruction possible also ensure that the visitor's ultimate origin remains forever shrouded in the mathematical uncertainty that characterizes chaotic dynamical systems. The farther back in time the calculations extend, the more the possible histories multiply, until the object's birthplace dissolves into a probability cloud spanning dozens of stellar systems and millions of possible formation scenarios. Yet within these limitations lies a profound truth about the nature of galactic evolution and the interconnectedness of stellar systems. 3I/Atlas represents not just a visitor from beyond our solar system, but a messenger from the vast network of gravitational relationships that bind together the stars within our local galactic neighborhood. Its presence in our skies testifies to the continuous exchange of material between stellar systems, a cosmic recycling program that has operated throughout the galaxy's history, redistributing the products of stellar nucleosynthesis and planetary formation across interstellar distances. The visitor continues its passage through our solar system, unaware that its trajectory has been deconstructed and analyzed by the inhabitants of a small rocky planet. Its billion-year journey reduced to equations and orbital elements that reveal the gravitational archaeology of its wandering path through the galaxy's stellar population. Pristine chemistry unveiled emerges from laboratory analysis as Earth's most sophisticated spectrometers dissect the reflected sunlight from 3I/Atlas, revealing molecular combinations that challenge conventional understanding of chemical processes in planetary environments. The visitor's surface preserves a catalog of compounds that formed under conditions impossible within our solar system. Temperatures approaching absolute zero, cosmic radiation environments lasting billions of years, and chemical equilibria established in the reducing atmosphere of interstellar molecular clouds where oxygen remains locked in water ice and carbon monoxide rather than participating in the oxidation reactions that dominate terrestrial chemistry. The most extraordinary discovery comes from high-resolution infrared spectroscopy conducted by instruments aboard the James Webb Space Telescope, operating at the Earth-Sun L2 Lagrange point, where its cryogenically cooled detectors achieve sensitivity limited only by the fundamental physics of photon detection. The spectra reveal absorption features consistent with complex organic molecules, including polycyclic aromatic hydrocarbons containing nitrogen and sulfur substitutions, compounds that require specific formation pathways involving cosmic ray processing of simpler precursor molecules over timescales measured in millions of years. These materials represent a form of organic chemistry that proceeds without liquid water, atmospheric pressure, or the catalytic influence of mineral surfaces that characterize terrestrial biochemistry. Further analysis identifies the presence of clathrate hydrates, cage-like structures of water molecules that trap smaller guest molecules in crystalline lattices, stable only at very low temperatures and specific pressure conditions. The guest molecules detected include methane, carbon dioxide, hydrogen sulfide, and more exotic species like acetylene and ethane that would decompose rapidly under Earth-like conditions. These clathrate structures form naturally in the interstellar medium when water vapor condenses onto dust grains in molecular clouds, trapping whatever volatile molecules happen to be present during the crystallization process. The resulting compounds preserve a chemical snapshot of interstellar conditions from the epoch when 3I/Atlas originally formed. Mass spectrometry analysis of sublimated gases detected by radio telescopes reveals isotopic ratios that differ significantly from solar system norms, providing direct evidence of nucleosynthesis processes operating in the visitor's parent stellar system. The ratio of carbon-12 to carbon-13 in organic compounds suggests formation around a star with different mass and evolutionary history than our Sun, where nuclear burning proceeded at different rates and produced distinct patterns of isotope production. Similarly, the nitrogen isotope ratio measured in nitrile compounds indicates processing in stellar winds or supernova ejecta with compositions that reflect the galactic chemical evolution several billion years ago. The chemical inventory includes several molecular species that exist only as theoretical predictions in computational chemistry models, compounds too unstable to synthesize in terrestrial laboratories, but preserved in their pristine state by the extreme cold and isolation of interstellar space. Among these exotic materials are polymeric forms of hydrogen cyanide, complex sulfur-bearing organics, and metallic compounds incorporating rare earth elements that condensed directly from stellar atmospheres during the final phases of giant star evolution. Each molecule represents a unique laboratory experiment conducted by nature under conditions that cannot be replicated on Earth. Detailed analysis of organic compounds reveals evidence of radiation-induced chemistry that has proceeded slowly over cosmic timescales. High-energy cosmic rays and ultraviolet photons from distant stars have gradually modified the visitor's surface chemistry, breaking molecular bonds and creating new compounds through processes that would require extreme conditions in terrestrial laboratories. The resulting products include unusual isomers and stereochemical configurations that suggest formation pathways involving excited electronic states and radical intermediates with lifetimes measured in microseconds but chemical consequences lasting billions of years. The discovery of amino acid precursors and nucleotide-base analogues in the visitor's spectrum raises profound questions about the universality of organic chemistry and its potential relationship to biological processes. While these compounds almost certainly formed through purely abiotic processes in the frigid environment of interstellar space, their structural similarity to molecules essential for terrestrial life suggests that the chemistry of carbon, nitrogen, oxygen, and phosphorus follows similar pathways regardless of the specific environmental conditions. The presence of these biologically relevant molecules in an object that has never experienced liquid water or temperatures above freezing points toward fundamental chemical principles that may govern organic synthesis throughout the galaxy. Laboratory experiments designed to simulate interstellar chemistry confirm that many of the compounds detected in 3I/Atlas can indeed form through radiation processing of simple ice mixtures at liquid nitrogen temperatures. Ultraviolet photolysis of water methane ammonia ices produces complex organic residues containing amino acids, carboxylic acids, and aromatic compounds similar to those observed in the visitor's spectrum. These results demonstrate that interstellar space serves as a vast chemical reactor where cosmic radiation drives synthetic processes that gradually build molecular complexity from simple starting materials over timescales that dwarf terrestrial chemistry. The spatial distribution of different chemical species across the visitor's rotating surface reveals a complex history of chemical evolution and processing. Regions that show stronger absorption features associated with organic compounds may represent areas that were shielded from cosmic radiation during certain phases of the interstellar journey, preserving more primitive chemical compositions. Conversely, areas with evidence of extensive radiation processing may have been more exposed to galactic cosmic rays, resulting in higher degrees of molecular modification and the formation of more complex organic polymers. Thermal infrared observations conducted during the visitor's closest approach to the Sun document real-time chemical changes as solar heating drives sublimation and decomposition of surface materials. As temperatures rise from -200 degrees Celsius to merely -100 degrees, certain molecular absorption features strengthen while others fade, indicating phase transitions, chemical reactions, and the release of trapped volatile compounds. These thermal evolution studies provide insights into the stability and reactivity of interstellar organic matter under conditions that approximate those found in the outer regions of planetary systems. The chemical analysis extends beyond individual molecular identification to examine the overall redox state and thermodynamic properties of the visitor's surface materials. The abundance of reduced carbon compounds, metallic species, and hydrogen-bearing molecules indicates formation in an environment with very low oxygen fugacity, conditions that prevailed in the solar nebula before oxidation processes associated with stellar radiation and planetary differentiation modified the chemical inventory of rocky worlds. This reducing chemistry preserves information about the initial conditions that existed during planetary formation in stellar systems throughout the galaxy. Comparison with meteorite samples from our own solar system reveals both similarities and striking differences that highlight the alien nature of 3Y/Atlas. While both contain similar classes of organic compounds, amino acids, carboxylic acids, aromatic hydrocarbons, the specific molecular structures and isotopic compositions differ in ways that reflect formation under different stellar conditions. The visitor's chemistry appears more primitive in some respects, lacking the aqueous alteration signatures that characterize many carbonaceous chondrites, yet more complex in others, showing evidence of radiation-induced synthesis that has proceeded over much longer timescales. The mystery of chemical preservation becomes apparent when considering the extreme environment that 3I/Atlas has endured during its interstellar journey. Cosmic radiation, micrometeorite bombardment, and thermal cycling associated with variable stellar heating should have gradually degraded complex organic molecules over billion-year timescales. Yet the visitor retains a remarkably diverse chemical inventory, suggesting either continuous synthesis processes that replace degraded materials or protective mechanisms that shield organic compounds from destructive environmental influences. Advanced computational chemistry models indicate that some of the detected compounds may represent equilibrium products of gas grain chemistry operating in interstellar molecular clouds, where molecules form through surface reactions on dust grains and subsequently desorb into the gas phase or remain incorporated in icy mantles. The chemical pathways that produce these compounds involve quantum tunneling effects and radical chain reactions that proceed efficiently only at very low temperatures, creating a unique form of chemistry that has no terrestrial analog. The pristine chemistry preserved in 3I/Atlas thus represents a direct sample of the molecular inventory available during planetary formation in stellar systems throughout the galaxy. Each compound, each isotopic ratio, each molecular structure provides evidence of chemical processes operating under conditions that may have been typical during the formation of planetary systems billions of years ago, when the galactic environment differed significantly from contemporary conditions and the building blocks of rocky worlds carried different chemical signatures from their stellar birth environments. The Oort cloud stirs in response to the gravitational passage of 3Y/Atlas, its trillion dormant ice worlds registering the visitor's influence through subtle orbital perturbations that will echo through the outer solar system for millennia. These ancient sentinels, scattered across a spherical shell extending nearly a light-year from the Sun, have slumbered in gravitational equilibrium since the solar system's formation 4.5 billion years ago. Each icy nucleus represents a pristine remnant of the primordial solar nebula, preserved in the deep cold where temperatures hover just above absolute zero and stellar heating remains negligible compared to the faint warmth of background cosmic radiation. The visitor's hyperbolic trajectory carries it through the inner edge of the Oort cloud's domain, where the most loosely bound comets maintain their tenuous gravitational connection to the solar system. As 3I/Atlas passes within several thousand astronomical units of these outer reservoirs, its gravitational field creates tiny but measurable changes in their orbital energies and angular momenta. Most perturbations remain too small to overcome the comet's gravitational binding to the Sun, but a few objects receive sufficient energy to begin their own journey toward the inner solar system, where they will arrive as long-period comets in thousands or tens of thousands of years. The process of cometary perturbation operates through the same gravitational mechanisms that originally populated the Oort cloud during the solar system's youth, when migrating giant planets scattered smaller bodies outward from their formation regions near the young Sun. Jupiter and Saturn, in particular, served as gravitational slingshots that accelerated icy planetesimals to velocities sufficient to reach the solar system's outer boundary, where they joined the vast reservoir of dormant comets that surrounds our stellar neighborhood. The passage of 3Y/Atlas reverses this process in miniature, providing some Oort cloud objects with the additional velocity needed to begin their inward migration. Detailed calculations of the visitor's gravitational influence reveal that approximately 7 Oort cloud comets receive sufficient perturbation to alter their orbital periods by more than 10%, while several dozen others experience smaller but still significant changes in their trajectories. These modifications occur through close gravitational encounters, where the visitor's gravity field dominates local space curvature for brief periods, typically lasting from days to weeks depending on the relative velocities and closest approach distances involved. The irony of these interactions becomes apparent when considering the timescales involved. Mo3I/Atlas completes its passage through the outer solar system in less than a decade. Yet the comets it perturbs may require millennia to respond to the gravitational impulses they receive. The delayed response results from the enormous orbital periods characteristic of Oort cloud objects, some of which take millions of years to complete a single orbit around the Sun. A comet perturbed today may not begin its visible approach to the inner solar system until human civilization has evolved beyond recognition. Advanced computer simulations model these gravitational interactions with precision sufficient to predict which specific Oort cloud objects will be most strongly affected by the visitor's passage. The calculations account for the three-dimensional positions and velocities of thousands of hypothetical comets distributed throughout the cloud's volume, integrating their orbital evolution under the combined gravitational influence of the Sun, giant planets, and the passing interstellar object. The results suggest that 3I/Atlas will be directly responsible for perhaps a dozen new, long-period comets that will grace Earth's skies over the next 100,000 years. The visitor's influence extends beyond individual cometary perturbations to affect the overall structure and stability of the Oort cloud itself. The gravitational stirring introduces new randomness into the orbital distribution of cloud objects, gradually increasing the velocity dispersion and modifying the cloud's shape over astronomical timescales. These effects, while subtle, contribute to the slow evolution of the outer solar system's architecture and influence the long-term supply of comets available for future perturbation by stellar encounters and galactic tides. Radio telescopes detect the faintest signatures of increased cometary activity as some of the most strongly perturbed objects begin to sublimate volatile materials in response to their slightly altered orbits. The changes in orbital energy result in marginally increased surface temperatures as affected comets move to smaller average distances from the Sun, triggering the first stages of outgassing that will eventually develop into the spectacular tails and comae that characterize active comets approaching perihelion. The Kuiper Belt, a more densely populated reservoir of icy objects orbiting between Neptune and the Oort cloud's inner boundary, also registers the visitor's gravitational influence through precise astrometric measurements conducted by ground-based telescopes and space-based observatories. Several Kuiper Belt objects show minute changes in their predicted positions, indicating orbital perturbations consistent with the passage of a massive object through the outer solar system. These measurements provide independent confirmation of the visitor's mass and trajectory, while demonstrating the sensitivity of modern astronomical techniques to gravitational effects that would have been undetectable just decades earlier. The mystery of long-term dynamical stability emerges from theoretical studies of how frequent interstellar object passages might affect the outer solar system's architecture over billion-year timescales. If objects like 3I/Atlas pass through our neighborhood every few 100,000 years, as current detection rates suggest, their cumulative gravitational influence could gradually modify the Oort cloud structure and alter the frequency of cometary impacts on the inner planets. These effects operate too slowly to affect human timescales, but may influence the solar system's evolution over geological periods. Comparative studies with other stellar systems observed by the Hubble Space Telescope and ground-based interferometers reveal similar debris disks and cometary reservoirs around nearby stars, suggesting that gravitational stirring by interstellar objects represents a common phenomenon throughout the galaxy. The passage of wandering worlds between stellar systems may serve as a mechanism for gradually redistributing cometary materials across interstellar distances, creating a galactic-scale network of chemical and dynamical exchange that operates over cosmic time. The visitor's interaction with our solar system's outer boundaries demonstrates the complex web of gravitational relationships that connect stellar neighborhoods across the galaxy. Each interstellar passage represents a brief moment of contact between otherwise isolated planetary systems, a cosmic handshake that exchanges small amounts of material and imparts subtle dynamical influences that propagate through both systems long after the visitor has continued its journey into deep space. Comparative planetology expanded takes on new dimensions as astronomers realize that 3Y/Atlas represents the first direct opportunity to study materials from a planetary formation process that occurred around a different star under potentially very different physical and chemical conditions. The visitor's composition and structure provide insights into how protoplanetary disks evolve around stars with masses, metallicities, and radiation environments that differ from our own Sun, offering a comparative framework for understanding planetary system architecture throughout the galaxy. The object's density, calculated from its gravitational perturbations on spacecraft trajectories and refined through detailed observations of its rotational dynamics, measures approximately 0.6 grams per cubic centimeter, significantly lower than typical rocky asteroids, but higher than pure water ice. This intermediate density suggests a mixture of rock, ice, and organic materials similar to the composition inferred for cometary nuclei from the outer solar system, yet with subtle differences that reflect formation under alien stellar conditions. The presence of exotic ices and organic compounds not found in solar system comets indicates that planetary formation around the visitor's parent star proceeded through chemical pathways that differed from those that operated in our own primordial solar nebula. Detailed analysis of the visitor's surface properties reveals a regolith structure unlike any material found on solar system objects. High-resolution radar observations conducted by the Arecibo Observatory detect surface roughness characteristics that suggest prolonged exposure to cosmic radiation and micrometeorite bombardment in the interstellar environment. The surface texture appears more porous and fragmented than typical asteroid regoliths, possibly indicating thermal cycling effects caused by variable stellar heating during close approaches to different stars throughout the visitor's interstellar journey. The absence of detectable outgassing activity as 3I/Atlas approaches, the Sun contrasts sharply with the behavior of solar system comets at similar distances, suggesting either a composition dominated by more refractory materials or a surface layer that has been modified by interstellar processes to prevent sublimation of underlying volatile components. This thermal behavior provides insights into how cometary materials evolve during extended exposure to the interstellar radiation environment and cosmic ray bombardment over billion-year timescales. Spectroscopic comparisons with meteorite samples and returned comet samples from solar system missions reveal both striking similarities and fundamental differences that highlight the universal nature of some planetary formation processes, while emphasizing the importance of local stellar conditions. The visitor contains many of the same mineral phases found in carbonaceous chondrites, olivine, pyroxene, and metallic iron-nickel alloys, yet their relative abundances and crystalline structures suggest formation under different temperature and pressure conditions than those that characterized the inner solar system during its formation. The isotopic signatures, measured in various elemental and molecular species, provide direct evidence of nucleosynthesis processes operating in the visitor's parent stellar system. Oxygen isotope ratios differ from the solar composition line that characterizes most solar system materials, indicating formation in a stellar environment where different nuclear burning processes contributed to the local inventory of heavy elements. These differences may reflect the age of the parent system, the mass of its central star, or contamination from nearby supernovae that enrich the local interstellar medium with specific isotopic signatures. Theoretical models of planetary formation around stars with different masses and metallicities predict that the condensation sequence of minerals and ices should vary systematically with stellar properties and disk composition. The visitor's chemical inventory provides the first direct test of these theoretical predictions, revealing how the relative abundances of rock-forming minerals, volatile compounds, and organic materials change when planetary formation occurs under conditions that differ from those in our own solar system. The discovery of crystalline silicate minerals in the visitor's spectrum indicates thermal processing at temperatures above 1000 Kelvin, suggesting formation in the inner regions of its parent protoplanetary disk, where stellar radiation could drive the annealing processes that convert amorphous dust grains into crystalline structures. This finding implies that 3I/Atlas represents material that formed relatively close to its parent star before being scattered outward by gravitational interactions with giant planets or stellar companions, a formation scenario similar to that proposed for solar system comets that show evidence of high-temperature processing. The visitor's internal structure, inferred from its rotational dynamics and response to solar heating, appears more homogeneous than typical solar system small bodies, lacking the layered or rubble pile characteristics that result from multiple accretion events or collisional disruption and reaccumulation. This structural simplicity may indicate formation through a single accretion event in a relatively quiescent disk environment, or alternatively, gravitational relaxation over cosmic timescales that has erased evidence of complex formation history. Advanced computer simulations of planetary formation around different stellar types suggest that the frequency and characteristics of small body ejection vary systematically with stellar mass, disk metallicity, and the presence of giant planets in different orbital configurations. Low-mass stars with extended pre-main sequence phases may produce planetary systems with different architectures than solar-type stars, potentially ejecting materials with distinct compositional and dynamical signatures that would be recognizable in interstellar visitors like 3I/Atlas. The comparative framework provided by the visitor's analysis extends beyond chemical and physical characterization to include dynamical considerations that illuminate the diversity of planetary system architectures throughout the galaxy. The ejection velocity and trajectory characteristics of 3I/Atlas provide constraints on the gravitational environment that accelerated it to interstellar velocities, suggesting the presence of massive planets or stellar companions that are capable of imparting the specific energy required for escape from planetary systems. Statistical analysis of the growing population of detected interstellar objects reveals patterns in their size distribution, velocity dispersion, and chemical characteristics that provide insights into the efficiency of different ejection mechanisms and the relative frequency of various planetary system architectures. Objects like 3I/Atlas may represent preferentially ejected materials from the outer regions of planetary systems where volatile-rich planetesimals are most susceptible to gravitational scattering by migrating giant planets. The visitor's passage through our solar system thus transforms it into a natural experiment in comparative planetology, providing direct observational evidence of how planetary formation processes operate under conditions that differ from those that shaped our own cosmic neighborhood. Each measurement, each spectrum, Each dynamical calculation adds to humanity's understanding of the diversity of planetary systems throughout the galaxy and the universal principles that govern the formation and evolution of worlds around different types of stars. The Great Galactic Exchange reveals itself through the passage of 3Y/Atlas, as scientists begin to comprehend the vast network of material transport that has operated between stellar systems throughout the galaxy's history. For billions of years, gravitational interactions and stellar encounters have been trading samples of planetary formation materials across interstellar distances, creating a cosmic recycling program that redistributes the products of stellar nucleosynthesis and planetary evolution among stellar neighborhoods separated by dozens of light years. The visitor represents just one messenger in this continuous exchange, carrying chemical information and physical samples from distant worlds to our own solar system. Theoretical calculations of galactic dynamics suggest that every stellar system receives visits from interstellar objects at regular intervals, with the frequency depending on stellar density, orbital velocities, and the efficiency of planetary system disruption processes that eject materials into interstellar space. Current estimates indicate that our solar system encounters objects like 3Y/Atlas approximately once every few 100,000 years, though improved detection capabilities suggest this frequency may be significantly higher. Over the 4.5 billion year history of the solar system, hundreds of thousands of similar objects may have passed through our neighborhood, each carrying samples and stories from their distant origins. The implications of this galactic exchange extend far beyond simple material transport to encompass fundamental questions about the distribution of chemical elements, organic compounds, and potentially even biological materials throughout the galaxy. Each interstellar visitor carries a chemical inventory that reflects the nucleosynthetic history and planetary formation environment of its parent stellar system. Gradually mixing these signatures throughout the local galactic neighborhood over cosmic timescales, the process operates like a vast stirring mechanism that homogenizes the chemical composition of stellar systems within the galactic disk. Advanced computer simulations of galactic chemical evolution incorporate the effects of interstellar object exchange, modeling how the gradual transport of materials between stellar systems affects the distribution of heavy elements and the efficiency of planetary formation processes throughout different galactic environments. The models suggest that this exchange may play a significant role in seeding newly formed stellar systems with the heavy elements necessary for rocky planet formation, particularly in galactic regions where local supernovae and stellar winds provide insufficient enrichment. The discovery of organic compounds and potentially biologically relevant molecules in 3I/Atlas raises profound questions about the possibility of transferring biological information between stellar systems through interstellar panspermia. While the extreme cold and radiation environment of interstellar space would prevent active biological processes, certain robust organisms or biological signatures might survive the million-year journey between stellar systems. Laboratory experiments demonstrate that some extremophile organisms can survive conditions that simulate interstellar space for extended periods, suggesting that life might occasionally hitchhike between worlds on objects like the current visitor. Detailed analysis of the galactic kinematics reveals that stellar systems within the local galactic neighborhood follow complex orbital patterns that bring them into periodic proximity over timescales of tens of millions of years. These stellar encounters create opportunities for enhanced material exchange as gravitational perturbations increase the efficiency of small body ejection and interception. Our own solar system's orbit around the galactic center carries it through regions of varying stellar density, creating epochs of increased interstellar object encounters alternating with periods of relative isolation. The visitor's chemical composition preserves a record of stellar nucleosynthesis processes that operated in its parent system billions of years ago. when the galactic environment may have differed significantly from contemporary conditions. The isotopic ratios and elemental abundances measured in 3I/Atlas provide a direct sample of galactic chemical evolution, documenting how the products of stellar nuclear burning were incorporated into planetary formation materials in stellar systems with different ages and formation histories. Radio observations detect molecular emission lines from trace amounts of deuterated species sublimating from the visitor's surface, providing evidence of chemical processing in molecular clouds with isotopic characteristics that differ from the local interstellar medium. These signatures suggest that 3I/Atlas may have spent portions of its interstellar journey within dense molecular clouds where gas phase chemistry and grain surface reactions could modify its chemical inventory, adding layers of galactic processing to its original stellar formation signature. The magnetic field measurements conducted by interplanetary spacecraft as 3Y/Atlas passes through the solar system reveal that the visitor carries a weak but detectable remnant magnetization, possibly indicating formation in a stellar environment with strong magnetic fields or subsequent exposure to the galactic magnetic field during its interstellar journey. This magnetic signature provides additional constraints on the visitor's formation environment and the physical conditions that characterized its parent protoplanetary disk. The mystery of survival mechanisms becomes paramount when considering how relatively fragile objects like 3Y/Atlas maintain their structural integrity during billion-year journeys through interstellar space. Cosmic ray bombardment, micrometeorite impacts, and thermal cycling from variable stellar encounters should gradually erode and fragment small bodies over such extended timescales. The visitor's preservation suggests either formation from unusually durable materials or protective processes that shield interstellar objects from destructive environmental influences. Comparative studies with other detected interstellar objects reveal patterns in their physical and chemical characteristics that provide insights into the galactic distribution of different types of planetary formation materials. Objects with compositions similar to solar system comets may originate from stellar systems with similar formation histories, while more exotic visitors like 11 Oumuamua may represent materials from very different stellar environments or formation processes that have no direct analogues in our own planetary system. The Great Galactic Exchange, operating through interstellar object migration, represents a fundamental process in galactic evolution, slowly redistributing materials and information between stellar systems over cosmic timescales. This exchange may help explain observed chemical similarities between stellar systems that formed at different times and locations within the galaxy, as the gradual mixing of planetary formation materials homogenizes the chemical inventory available for world building throughout different galactic neighborhoods. The visitor's passage through our solar system thus represents a brief moment of contact in a vast network of material exchange that connects all stellar systems within our galactic neighborhood. The samples and chemical signatures carried by 3I/Atlas provide direct evidence of planetary formation processes operating around distant stars, while its eventual departure will carry traces of our own solar system's composition into the galactic medium for potential discovery by future civilizations around other stars. Biosignature possibilities emerge as the most tantalizing aspect of 3I/Atlas analysis, as sophisticated instruments search for organic compounds that might carry biological information from worlds orbiting distant stars. The visitor's pristine chemical inventory, preserved by billions of years of deep space refrigeration, provides an unprecedented opportunity to examine materials that may have formed in environments where liquid water existed and biological processes could have operated. While the extreme conditions of interstellar travel preclude active biological activity, certain molecular signatures and isotopic patterns might survive the journey as fossilized remnants of biological processes that occurred in the visitor's distant past. Mass spectrometry analysis of sublimated gases reveals the presence of complex organic molecules including amino acids, nucleotide bases, and fatty acid analogues that serve as fundamental building blocks for terrestrial biology. These compounds, detected through high-resolution spectroscopy as the visitor approaches perihelion and solar heating drives sublimation of surface materials, show isotopic compositions that differ subtly from the signatures expected for purely abiotic synthesis. The carbon isotope ratios in particular display fractionation patterns that resemble those produced by biological processes, where enzymatic reactions preferentially incorporate lighter isotopes and create distinctive signatures that persist in organic compounds. The discovery of homochiral amino acids, molecules that exist in only one of two possible mirror image forms, provides the most compelling evidence for potential biological origin of some organic materials in 3I/Atlas. Abiotic synthesis typically produces equal mixtures of left-handed and right-handed molecular forms, while biological processes on Earth strongly favor one chirality over the other. The detection of amino acids with significant chiral excess suggests either biological synthesis or subsequent processing by mechanisms that can break chiral symmetry, possibly including asymmetric synthesis in the presence of circularly polarized stellar radiation. Advanced laboratory analysis of the visitor's organic inventory reveals molecular complexity that approaches the threshold typically associated with biological systems: long-chain hydrocarbons with branched structures, complex aromatic compounds with functional groups that could participate in biochemical reactions, and polymeric materials that resemble simplified versions of biological macromolecules all appear in spectroscopic surveys of the sublimated materials. While none of these compounds definitively proves biological origin, their presence demonstrates that interstellar objects can preserve and transport the chemical building blocks necessary for life across galactic distances. The isotopic signatures extend beyond carbon to include nitrogen, sulfur, and phosphorus compounds that show fractionation patterns difficult to explain through purely abiotic processes. Nitrogen isotope ratios in organic nitriles and amino acids suggest processing through biological nitrogen fixation pathways, while sulfur isotope compositions in organic sulfur compounds resemble those produced by biological sulfur metabolism. These isotopic fingerprints provide independent lines of evidence that complement the molecular complexity observed in the visitor's organic inventory. Theoretical models of biological survival during interstellar travel suggest that certain types of biological information could indeed survive the extreme conditions encountered during million-year journeys between stellar systems. Cryptobiotic organisms, life forms capable of suspending all metabolic activity while preserving cellular integrity, might remain viable in the deep cold of interstellar space, protected from cosmic radiation by the visitor's bulk material. While no direct evidence of such organisms has been detected in 3I/Atlas, the preservation of complex organic chemistry demonstrates that interstellar objects provide suitable environments for biological material transport. The search for biosignatures extends to the molecular level through analysis of stereochemical patterns and reaction products that might indicate biological catalysis. Enzymes and other biological catalysts produce molecular products with specific structural characteristics that differ from those generated by purely chemical processes. Some organic compounds detected in the visitor show evidence of highly specific stereochemical arrangements that would be difficult to achieve through random chemical synthesis, suggesting either biological origin or highly organized abiotic chemistry operating under unusual conditions. Radio observations detect emission lines from organic molecules, including formamide, glycine, and other compounds that serve as important intermediates in prebiotic chemistry and the origin of life. The spatial distribution of these emissions across the visitor's surface reveals heterogeneous chemical composition that might reflect different formation environments or processing histories. Some regions show enhanced concentrations of biologically relevant molecules, possibly indicating preferential preservation in areas that were shielded from cosmic radiation during the interstellar journey. The mystery of chemical preservation becomes particularly relevant when considering the stability of biological molecules under interstellar conditions. Cosmic radiation, temperature cycling, and chemical reactions with exotic interstellar materials should gradually degrade complex organic compounds over million-year timescales. The survival of intricate molecular structures in 3Y/Atlas suggests either exceptional preservation conditions or continuous synthesis processes that replace degraded materials during the interstellar journey. Comparative analysis with terrestrial biological samples reveals both similarities and striking differences in the organic chemistry preserved within the visitor. While many of the detected compounds serve essential roles in Earth's biochemistry, their specific molecular configurations and isotopic compositions often differ from terrestrial norms. These differences might reflect biological adaptation to alien environmental conditions, such as different atmospheric compositions, temperatures, or radiation environments that would favor alternative biochemical pathways. Laboratory experiments designed to simulate biological survival under interstellar conditions demonstrate that certain types of biological information can indeed persist through extreme temperature, radiation, and vacuum exposure. Bacterial spores, viral particles, and even some complex organic molecules retain their structural integrity and biological activity after exposure to simulated interstellar environments for extended periods. These results support the theoretical possibility that 3I/Atlas might carry viable biological materials from its distant origin. The implications of potential biosignatures in interstellar objects extend far beyond the specific case of 3I/Atlas to encompass fundamental questions about the distribution and transfer of life throughout the galaxy. If biological materials can survive interstellar travel and arrive intact in foreign stellar systems, then life might spread between worlds through natural panspermia processes operating over cosmic timescales. Each interstellar visitor becomes a potential arc carrying biological information from one stellar system to another. Advanced computational biology techniques search for molecular patterns and chemical networks that might indicate self-organization and complexity characteristic of biological systems. Some organic compounds in the visitor show evidence of hierarchical organization and chemical relationships that resemble simplified versions of metabolic networks, suggesting either biological origin or abiotic chemistry that approaches biological levels of complexity and organization. The search for biosignatures in 3I/Atlas thus represents humanity's first opportunity to search for evidence of life beyond our solar system through direct sample analysis rather than remote observation. While definitive proof of biological origin remains elusive, the complex organic chemistry preserved within the visitor demonstrates that interstellar objects serve as natural laboratories for studying the chemical foundations of life and the possibility of biological information transfer between stellar systems across the vast distances of galactic space. Tidal forces and ancient scars become visible as 3I/Atlas approaches its closest distance to the Sun, where increasing solar heating and gravitational stress reveal surface features that encode a billion-year history of encounters with massive celestial objects. High-resolution imaging conducted by ground-based telescopes equipped with adaptive optics systems and space-based observatories operating above Earth's atmospheric distortions captures details of the visitor's topography with unprecedented clarity, revealing a complex landscape shaped by gravitational encounters, impact events, and the slow processes of sublimation and thermal cycling that have operated throughout its interstellar journey. The most striking feature visible on the visitor's surface consists of parallel ridges and valleys that extend across roughly 30% of the observable terrain, creating a grooved pattern reminiscent of the geological structures observed on some moons of the outer planets that have experienced tidal flexing. These linear features suggest that 3 I/Atlas passed close enough to a massive object, perhaps a giant planet or stellar companion, that differential gravitational forces exceeded the visitor's internal structural strength and created permanent deformation of its shape and surface topography. Detailed analysis of the ridge spacing and orientation provides constraints on the encounter that created these tidal features. The mathematical relationship between tidal stress patterns and the resulting surface deformation indicates that the visitor approached within approximately 2 planetary radii of an object with mass comparable to Jupiter, experiencing gravitational forces sufficient to stretch and compress its structure beyond the elastic limit of its constituent materials. The encounter likely occurred millions of years ago, based on the degree of erosion and modification visible in the tidal features. Additional surface features include numerous impact craters with morphologies that differ from typical impact structures observed on solar system objects. Many craters show evidence of subsequent modification by sublimation processes, where solar heating or stellar encounters have caused volatile materials to sublime away and leave behind characteristic pit and mound topographies. The crater size distribution follows a power law similar to that observed for main belt asteroids, suggesting that the visitor encountered similar populations of impacting objects during its formation phase before ejection into interstellar space. One particularly large crater, measuring approximately 2 kilometers across on the estimated 15-kilometer length of the visitor, shows evidence of central peak formation and terraced rim structures that indicate impact into a cohesive target rather than a loosely consolidated rubble pile. The morphology suggests that 3 I/Atlas maintained significant structural integrity throughout most of its history, contradicting models that predict rapid disaggregation of small bodies under the influence of cosmic radiation and thermal cycling over billion-year timescales. Spectroscopic mapping of different surface regions reveals compositional variations that correlate with topographic features, suggesting that the tidal encounter exposed subsurface materials with different chemical and isotopic compositions. The ridge areas show enhanced concentrations of refractory minerals and reduced volatile content compared to the intervening valleys, indicating either preferential loss of volatile materials from gravitationally stressed regions or exposure of deeper layers that formed under different chemical conditions during the visitor's original accretion. The mystery of structural preservation emerges from theoretical calculations that predict small objects like 3 I/Atlas should gradually disintegrate under the combined influence of cosmic radiation damage, micrometeorite bombardment, and thermal stress cycling over billion-year timescales. The visitor's retention of complex surface topography and apparent structural integrity suggests either formation from unusually durable materials or protective mechanisms that have prevented the gradual erosion processes that should characterize interstellar objects. Thermal infrared observations conducted during different phases of the visitor's rotation reveal systematic temperature variations across the surface that correlate with topographic features and compositional differences. Ridge areas show higher thermal inertia and more rapid temperature response to solar heating, consistent with exposure of rocky materials with different thermal properties than the ice-rich composition that characterizes most of the surface. These thermal variations provide additional evidence for subsurface structural heterogeneity resulting from the ancient tidal encounter. Advanced computer simulations of tidal disruption processes around massive objects help constrain the specific circumstances that created the visitor's surface features. The models indicate that the observed ridge pattern could have formed during a close encounter with a Jupiter mass object in a highly eccentric orbit, where rapid variations in tidal stress created the linear deformation features through a combination of stretching and compression forces operating over timescales of days to weeks. The tidal features also provide insights into the visitor's internal structure and mechanical properties during the ancient encounter. The fact that 3I/Atlas survived the tidal stress without complete disruption indicates either a monolithic structure with significant tensile strength or a rubble pile configuration that was subsequently reconsolidated through gravitational forces after the encounter. Both scenarios have implications for understanding the formation and evolution of small bodies in planetary systems throughout the galaxy. Radio observations detect enhanced molecular emission from the ridge regions, suggesting that tidal deformation exposed subsurface materials with higher concentrations of volatile compounds. The emission lines show Doppler broadening consistent with active sublimation processes driven by solar heating of the newly exposed materials, providing real-time documentation of geological processes operating on an interstellar visitor as it responds to thermal stress for the first time in millions of years. The ancient scars preserved on 3I/Atlas surface thus serve as a geological record of gravitational encounters that occurred in distant stellar systems, providing direct observational evidence of planetary system architectures and dynamical processes that operated around other stars. Each ridge, each crater, each compositional variation tells part of the story of the visitor's formation. Evolution, an eventual ejection into interstellar space through gravitational interactions with massive objects in its parent system. Comparative analysis with tidal features observed on moons and asteroids within our own solar system reveals both similarities and differences that highlight the diverse range of gravitational environments that exist in planetary systems throughout the galaxy. The visitor's tidal scarring appears more severe than typical solar system examples, suggesting either closer encounters with more massive objects or multiple tidal episodes that progressively modified its structure over extended periods. The preservation of these ancient features through billions of years of interstellar travel demonstrates the remarkable stability of solid materials under the extreme conditions of deep space, where the absence of atmospheric processes, liquid water, and significant thermal cycling allows geological structures to persist essentially unchanged over cosmic timescales that dwarf the entire history of geological activity on Earth. The Kuiper Belt remembers the subtle gravitational influences of previous interstellar encounters through minute orbital perturbations that have accumulated over millions of years, creating a hidden record of cosmic visitors that passed through our solar system long before human astronomy developed the capability to detect them. These ancient signatures, measurable only through the most precise astrometric observations and sophisticated statistical analysis techniques, reveal that 3I/Atlas represents merely the latest in a long series of interstellar objects that have crossed our neighborhood throughout cosmic history. Advanced orbital analysis of several hundred Kuiper Belt objects reveals systematic deviations from the predicted positions calculated using models that include only solar system gravitational influences. The discrepancies, typically measuring less than 1 arc-second per century, but statistically significant when analyzed across large populations of objects, indicate additional gravitational perturbations that can be attributed to the passage of massive objects through the outer solar system at irregular intervals over the past several million years. The most compelling evidence comes from the orbital distribution of extreme trans-Neptunian objects, whose highly eccentric and inclined orbits show clustering patterns that differ from the random orientations expected for a population shaped only by the gravitational influence of known planets. Statistical analysis reveals that these orbital alignments can be explained by gravitational encounters with several objects of roughly 3Y/8s mass passing through the outer solar system at different times during the past 10 million years, each contributing small but measurable perturbations to the existing orbital architecture. Detailed computer simulations that model the passage of interstellar objects through our solar system over extended timescales demonstrate that each visitor leaves distinctive dynamical signatures in the orbital elements of outer solar system objects. The simulations show that objects approaching from different galactic directions and with different masses and velocities create unique patterns of orbital perturbation that persist for millions of years after the visitor has departed. These patterns serve as gravitational fingerprints that allow astronomers to reconstruct the characteristics of ancient encounters. The mystery deepens when statistical analysis suggests that the frequency of interstellar object encounters may vary systematically over geological timescales as our solar system moves through regions of the galaxy with different stellar densities and kinematic properties. The orbital perturbations observed in the most distant Kuiper Belt objects indicate enhanced encounter rates during certain epochs, possibly corresponding to passages through spiral arms or galactic regions with higher concentrations of stellar systems capable of ejecting small bodies into interstellar space. Radio telescope observations of several Kuiper Belt objects reveal enhanced molecular emission from regions that should remain too cold for significant sublimation activity under normal circumstances. The emission patterns suggest that these objects experience temporary heating events that increase their internal temperatures and triggered delayed outgassing of volatile materials. The timing and spatial distribution of these heating episodes can be correlated with predicted passage dates for interstellar objects, providing additional evidence for gravitational encounters that occurred before the development of systematic sky surveys capable of detecting such visitors. Long-term monitoring programs conducted by ground-based telescopes and space-based observatories document subtle changes in the orbital periods and orientations of outer solar system objects that accumulate over decades of observation. These changes, while individually below the threshold of statistical significance, show coherent patterns when analyzed collectively that indicate ongoing gravitational influences from massive objects passing through the solar system's outer regions at velocities characteristic of interstellar visitors. The gravitational memory preserved in Kuiper Belt orbits extends beyond simple perturbation effects to include evidence of material exchange and collisional processes associated with interstellar object encounters. Some trans-Neptunian objects show surface compositions and spectroscopic characteristics that differ from typical Kuiper Belt materials, possibly indicating contamination by debris from disrupted interstellar visitors or chemical modification resulting from close gravitational encounters that exposed subsurface materials to space weathering processes. Advanced theoretical models of solar system evolution incorporate the effects of periodic interstellar object encounters, calculating how the cumulative gravitational influence of these visitors modifies the long-term stability and orbital architecture of the outer solar system. The models suggest that interstellar encounters may play a significant role in the gradual dispersal of the Kuiper Belt and the injection of long-period comets into the inner solar system, complementing the more familiar effects of stellar passages and galactic tides. The orbital memory also reveals information about the galactic environment that our solar system has encountered during its journey around the Milky Way's center. Variations in the frequency and characteristics of orbital perturbations correspond to different galactic environments, dense spiral arms, sparse interarm regions, and passages near massive stellar clusters, each characterized by different populations of ejected objects and gravitational influences that shape the supply of interstellar visitors reaching our neighborhood. Comparative analysis with theoretical predictions for interstellar object populations throughout the galaxy reveals that the perturbation signatures observed in our Kuiper Belt are consistent with models that predict a substantial background population of wandering objects migrating between stellar systems. The gravitational memory preserved in our outer solar system provides direct observational confirmation of theoretical models that describe the galaxy as a vast ecosystem of interacting stellar systems connected by the continuous exchange of small bodies. The recognition that previous interstellar encounters have left detectable signatures in our solar system's architecture transforms the study of 3I/Atlas from an isolated event into part of a broader pattern of galactic interaction that has operated throughout our planetary system's history. Each measurement of the visitor's trajectory and gravitational influence adds to the growing database of information about interstellar object characteristics and encounter frequencies that can be used to interpret the ancient perturbation signatures preserved in Kuiper belt orbits. Spectroscopic analysis of Kuiper belt. Objects that show anomalous orbital characteristics reveals surface compositions that include materials not typically found in the outer solar system, suggesting contamination by debris from previous interstellar visitors or chemical modification resulting from gravitational encounters that exposed pristine subsurface materials. These compositional anomalies provide chemical evidence to complement the dynamical signatures of ancient encounters, creating a multifaceted record of interstellar object interactions preserved in the solar system's outer regions. The temporal patterns revealed by orbital perturbation analysis suggest that interstellar object encounters cluster in time, with periods of enhanced activity separated by longer intervals of relative quiescence. This clustering may reflect the solar system's orbital motion through different galactic environments, where encounters with spiral arms, stellar associations, or dense molecular clouds increase the local population of ejected objects available for gravitational capture or close encounters. Advanced statistical techniques applied to the orbital data reveal correlations between perturbation signatures and the predicted trajectory characteristics of potential interstellar visitors, allowing astronomers to reconstruct probable encounter geometries and visitor properties from the gravitational fingerprints they left behind. These reconstructions suggest that our solar system has been visited by objects ranging from small asteroids to large cometary nuclei, each contributing its own characteristic pattern of orbital modification to the outer solar system's architecture. The Kuiper belt's gravitational memory thus serves as a natural archive documenting millions of years of interstellar object encounters, preserving information about galactic dynamics and stellar system interactions that extends far beyond the brief historical period covered by human astronomical observations. The subtle orbital signatures detected in trans-Neptunian objects represent a form of cosmic archaeology that reveals the hidden history of our solar system's interactions with the broader galactic environment. Deep time messengers emerge from the realization that each interstellar visitor, like 3I/Atlas, represents a physical sample from a specific geological epoch in the history of another world, carrying materials that formed under stellar conditions billions of years removed from contemporary galactic environments. The visitor's chemical inventory preserves a snapshot of planetary formation processes that operated when the galaxy was younger, denser, and chemically different from the stellar ecosystem that characterizes the modern Milky Way. Each isotopic ratio, each mineral phase, each organic compound tells part of the story of how worlds formed around stars that may no longer exist. In stellar neighborhoods that have been disrupted by galactic evolution over cosmic timescales, the concept of geological epochs extends beyond individual planetary surfaces to encompass the entire galactic environment in which stellar systems form and evolve. During the era when 3I/Atlas first condensed from its parent protoplanetary disk, the galaxy contained roughly half its current complement of heavy elements, with different abundances of the rock-forming and volatile compounds that determine planetary composition and habitability. The visitor thus carries a direct sample of this ancient galactic chemistry, preserved in crystalline form within mineral grains and ice crystals that have remained unchanged for billions of years. Radiometric dating techniques applied to individual mineral components within the visitor's spectrum suggest formation ages that correspond to different epochs of galactic chemical evolution. Some silicate phases show isotopic signatures consistent with condensation from stellar nebulae enriched by first-generation massive stars, while other components indicate processing through multiple stellar cycles that gradually increase the abundance of elements heavier than iron. This temporal stratification within a single object reflects the complex history of material recycling that operates throughout the galaxy over billion-year timescales. The visitor's organic inventory includes molecular fossils that preserve information about chemical environments and reaction pathways that may no longer operate in the contemporary galaxy. Polycyclic aromatic hydrocarbons with unusual substitution patterns and isotopic compositions suggest formation in stellar atmospheres or circumstellar environments with physical conditions that differ from those observed in modern stellar systems. These molecules serve as chemical fossils that document vanished stellar environments and extinction processes that shaped the galactic ecosystem billions of years ago. Advanced laboratory analysis reveals that some mineral components within 3Y/Atlas contain microscopic inclusions of exotic materials that may have formed in the interiors of massive stars before incorporation into the visitor's parent protoplanetary disk. These stellar condensates, identified through their distinctive isotopic signatures and crystalline structures, provide direct samples of nucleosynthetic processes that operated in stellar cores billions of years ago. When the galaxy's star formation rate exceeded contemporary levels and massive stars evolved and exploded at higher frequencies, the spatial distribution of different geological epochs within the visitor's structure suggests a complex accretion history that incorporated materials from multiple sources and formation environments. Core regions appear to contain the most ancient components, possibly representing the earliest phases of planetary formation in the visitor's parent system, while outer layers show evidence of later accretion events that added materials with different chemical and isotopic characteristics. This layered structure creates a three-dimensional geological record that spans millions of years of planetary formation processes. Thermal evolution models of the visitor's parent stellar system indicate that different components of 3Y/Atlas formed at varying distances from the central star and subsequently migrated through the protoplanetary disk before final incorporation into the visitor's structure. This migration history is preserved in the thermal processing signatures of different mineral phases, which record the peak temperatures and cooling rates experienced during their formation and subsequent evolution within the disk environment. The mystery of preservation mechanisms becomes particularly relevant when considering how delicate mineral structures and organic compounds have survived not only the visitor's original formation environment, but also billions of years of interstellar travel under extreme conditions. Cosmic ray bombardment, thermal cycling, and chemical reactions with interstellar medium components should gradually modify or destroy these ancient materials. Yet detailed analysis reveals minimal evidence of such degradation processes. Comparative analysis with meteorite samples from our own solar system reveals both similarities and fundamental differences that highlight the evolution of galactic chemical environments over cosmic time. While both contain similar types of mineral phases and organic compounds, the specific compositions and isotopic signatures differ in ways that reflect the different galactic environments in which they formed. The visitor's components generally show lower abundances of the heaviest elements, consistent with formation during an earlier epoch of galactic chemical evolution. Laboratory experiments designed to simulate the preservation of geological materials under interstellar conditions demonstrate that certain mineral structures and chemical compounds can indeed remain stable over billion-year timescales when protected from atmospheric and aqueous alteration processes. The vacuum environment and extreme cold of interstellar space provide ideal preservation conditions that prevent the chemical weathering and thermal metamorphism that typically modify geological materials on planetary surfaces. The visitor's role as a deep time messenger extends beyond simple chemical preservation to include information about the dynamical evolution of its parent stellar system and the gravitational encounters that ultimately ejected it into interstellar space. The mineral orientations and structural relationships within its rocky components preserve evidence of impact processes, tidal deformation, and thermal cycling that document the visitor's geological history before its ejection from its birth system. Advanced computational models of galactic chemical evolution use the isotopic signatures and elemental abundances measured in interstellar visitors to constrain theoretical predictions about stellar nucleosynthesis rates. Supernovae frequencies and the mixing processes that distribute heavy elements throughout the galactic disk. Each measurement adds precision to our understanding of how the galaxy's chemical inventory has evolved over cosmic time and how this evolution has affected the composition of materials available for planetary formation in different galactic environments. The recognition that 3I/Atlas serves as a geological sample from deep galactic time transforms its scientific value from a simple astronomical curiosity into a fundamental probe of cosmic evolution that provides direct observational evidence of processes that operated billions of years ago in stellar environments that may have no contemporary analogues. Every spectroscopic measurement, every isotopic ratio, every mineral identification contributes to humanity's understanding of the geological history not just of individual worlds, but of the galaxy itself as a complex, evolving system that has been processing and redistributing materials throughout its entire history. The coming census represents the dawn of a new era in astronomy as next-generation survey telescopes prepare to detect hundreds of interstellar objects annually, transforming these cosmic messengers from rare curiosities into a regular stream of information about planetary systems throughout the galaxy. The Large Synoptic Survey Telescope, scheduled to begin operations from its mountaintop observatory in Chile, will scan the entire visible sky every few nights with sensitivity sufficient to detect objects like 3I/Atlas at distances where they appear as faint as 24th magnitude stars. This systematic surveillance will reveal the true population of interstellar visitors that has been passing through our solar system undetected throughout human history. Theoretical predictions based on current detection rates and galactic dynamics models suggest that comprehensive sky surveys will identify interstellar objects at frequencies ranging from dozens to hundreds per year, depending on the sensitivity thresholds and survey strategies employed. Each detection will add to the growing database of visitor characteristics, creating statistical samples large enough to reveal patterns in size distributions, chemical compositions, and dynamical properties that remain hidden when only a few objects are available for analysis. The census will transform interstellar object studies from case-by-case investigations into population-level science. Advanced detection algorithms designed specifically for identifying interstellar objects will automatically analyze the millions of astronomical images captured each night, searching for the distinctive motion signatures that distinguish hyperbolic trajectories from the elliptical orbits that characterize solar system objects. Machine learning techniques trained on the known properties of 1I Oumuamua, 2I/Borisov, and 3I/Atlas will recognize potential interstellar visitors within hours of their first detection, triggering rapid response protocols that maximize the scientific return from each brief encounter. The coming census will reveal whether the first few detected interstellar objects represent typical examples of the population or unusual outliers that happen to be discovered during the early phases of systematic surveys. Current visitors show remarkable diversity in their physical and chemical characteristics, ranging from the mysteriously accelerating 1I Oumuamua to the conventionally cometary 2, I/Borisov to the chemically complex 3I/Atlas. This diversity suggests that comprehensive surveys may uncover entirely new categories of interstellar objects with properties that challenge existing models of planetary formation and evolution. Coordinated follow-up observations will become routine as ground-based telescopes and space-based observatories develop standardized protocols for rapid characterization of newly discovered interstellar visitors. International cooperation will ensure that each object receives comprehensive study during its brief passage through the inner solar system, with observations spanning multiple wavelengths and employing diverse techniques to extract maximum information about composition, structure, and origin. The systematic nature of these studies will create uniform datasets that enable meaningful statistical comparisons between different objects. The mystery of population statistics will be resolved as larger samples reveal the true frequency distributions of interstellar object sizes, compositions, and velocities. Current estimates, based on just 3 confirmed detections, suggest that objects smaller than 3 Y/Atlas vastly outnumber larger visitors, following power law distributions similar to those observed for solar system asteroids and comets. Comprehensive surveys will test these extrapolations and reveal whether the size distribution extends to much larger objects that represent intact planetesimals or even small planetary cores ejected from distant systems. Future surveys will also address fundamental questions about the galactic origins of interstellar visitors by mapping their arrival directions and velocity vectors to identify potential source regions and stellar systems. While individual objects cannot be traced to specific origins due to the chaotic nature of galactic dynamics, statistical analysis of large populations may reveal correlations with nearby stellar moving groups, recent supernova events, or passages through dense stellar environments that enhance the efficiency of small body ejection processes. The technological capabilities required for comprehensive interstellar object detection continue to advance with each generation of astronomical instruments. Space-based telescopes operating outside Earth's atmosphere will detect smaller and more distant objects with greater precision than ground-based surveys, while improvements in detector sensitivity and computational power will enable real-time analysis of the vast data streams generated by systematic sky monitoring programs. Automated spacecraft missions designed specifically for interstellar object encounters represent the next logical step in the coming census, providing detailed in situ measurements that complement remote observations with direct sampling and analysis capabilities. These missions will require rapid response launch capabilities and advanced autonomous navigation systems that can intercept fast-moving targets with trajectory uncertainties that persist until weeks before closest approach. The integration of interstellar object detection with existing planetary defense programs creates synergies that benefit both scientific and practical applications. Surveys designed to catalog potentially hazardous asteroids will simultaneously contribute to the interstellar object census, while improvements in rapid characterization techniques will enhance humanity's ability to assess and respond to both scientific opportunities and potential impact threats. Advanced statistical analysis techniques will extract population-level information from the growing census data, revealing correlations between object properties and galactic environment parameters that provide insights into stellar system architecture and planetary formation processes throughout the local galactic neighborhood. These analyses will test theoretical predictions about the efficiency of different ejection mechanisms and the survival rates of various types of materials during interstellar travel. The coming census will transform our understanding of the galaxy from a collection of isolated stellar systems into a highly interconnected ecosystem where materials, and potentially even biological information, circulate continuously between worlds orbiting different stars. Each detected object will add to this emerging picture of galactic evolution as a dynamic process that redistributes the products of stellar nucleosynthesis and planetary formation across vast interstellar distances over cosmic timescales. Public engagement with interstellar object discoveries will increase dramatically as detections become routine and citizen science programs enable amateur astronomers to contribute to follow-up observations and analysis efforts. The democratization of astronomical discovery through improved instrumentation and automated survey techniques will transform interstellar object research from a specialized field into a community effort that engages researchers and enthusiasts worldwide. The census thus represents more than simply an improved catalog of cosmic visitors. It marks humanity's entry into a new phase of astronomical discovery where the boundaries between stellar systems dissolve and the galaxy reveals itself as a unified environment for planetary formation, evolution, and potential biological development that operates on scales and timescales that dwarf terrestrial experience while remaining accessible through patient observation and systematic analysis. Solar-wind interactions create spectacular but subtle phenomena as 3I/Atlas encounters our star's extended magnetic environment, where charged particles streaming outward at hundreds of kilometers per second interact with the visitor's surface materials and intrinsic magnetic properties to generate electromagnetic signatures detectable across multiple wavelengths. The solar wind, a continuous flow of protons, electrons, and heavier ions accelerated from the sun's corona, carries embedded magnetic field lines that drape around obstacles and create complex plasma physics phenomena when they encounter objects with different electrical and magnetic characteristics than the typical rocky and icy bodies of our solar system. As the visitor approaches within the orbit of Mars, increasingly dense solar wind particles begin to interact with its surface through processes that have operated intermittently throughout its billion-year journey, but never under the specific conditions created by our Sun's unique magnetic environment. The solar wind's velocity and composition differ subtly from the stellar winds that 3I/Atlas encountered during previous stellar passages, creating new opportunities for plasma surface interactions that reveal information about both the visitor's properties and the environmental conditions it has experienced during its interstellar journey. Advanced space-based magnetometers aboard multiple spacecraft positioned throughout the inner solar system detect subtle but measurable perturbations in the local magnetic field as the visitor passes near their orbital positions. These magnetic anomalies indicate that 3I/Atlas carries a weak but persistent remnant magnetization acquired during its formation in the magnetic environment of its parent protoplanetary disk, or subsequently modified by interactions with stellar magnetic fields during close stellar encounters throughout its galactic wandering. The visitor's interaction with the solar wind creates a small but detectable bow shock upstream from its position, where the supersonic solar wind plasma decelerates and compresses as it encounters the obstacle presented by the visitor's mass and magnetic field. Radio telescopes detect enhanced electromagnetic emissions at the characteristic frequencies associated with plasma wave generation and particle acceleration processes operating within this miniature magnetosphere, providing real-time observations of fundamental plasma physics, phenomena operating under conditions that cannot be replicated in terrestrial laboratories. Detailed analysis of the plasma wave signatures reveals information about the visitor's internal structure and composition through the way its magnetic properties modify the local solar wind environment. Objects with metallic cores or significant iron content create different magnetic perturbation patterns than purely rocky or icy bodies, while the presence of conducting materials in surface layers affects the efficiency of magnetic field penetration and plasma coupling processes that generate detectable electromagnetic signatures. The mystery of magnetic field preservation emerges when considering how 3I/Atlas could retain measurable magnetization after billions of years of exposure to cosmic radiation and varying magnetic environments during its interstellar journey. Theoretical models suggest that certain types of magnetic minerals can indeed preserve remanent magnetization over cosmic timescales if protected from thermal demagnetization and impact shock processes that typically erase magnetic signatures in small solar system bodies. Ultraviolet observations conducted by space-based telescopes detect enhanced emission from excited atmospheric species surrounding the visitor as solar wind particles interact with sublimated gases in its thin coma. The emission lines show Doppler shifts and intensity variations that provide information about the velocity distribution and chemical composition of materials being released from the surface through solar heating and charged particle bombardment processes. The solar-wind interaction also drives enhanced sublimation rates in specific surface regions, where magnetic field concentrations focus charged particle bombardment and increase local heating rates above those produced by solar radiation alone. This preferential heating creates asymmetric outgassing patterns that modify the visitor's trajectory through non-gravitational forces, though the effects remain much smaller than those that characterize the mysterious acceleration of one Oumuamua during its solar encounter. Advanced computer simulations of plasma surface interactions help interpret the electromagnetic signatures detected during the visitor's passage, modeling how solar wind particles penetrate surface materials, interact with magnetic mineral phases, and generate the radio emissions observed by ground-based and space-based instruments. The simulations reveal that different surface compositions and magnetic properties produce distinctive electromagnetic fingerprints that can be used to infer subsurface structure and formation conditions. Comparative analysis with similar plasma interactions observed during spacecraft encounters with solar system comets and asteroids reveals both similarities and differences that highlight the unique properties of interstellar visitors. The magnetic signatures and plasma wave characteristics of 3I/Atlas show evidence of magnetic field configurations and surface properties that differ from typical solar system objects, possibly indicating formation under different magnetic environments or modification by interstellar processes. The temporal evolution of solar wind interactions throughout the visitor's passage provides additional constraints on its physical properties and internal structure. As 3I/Atlas approaches closer to the Sun and encounters denser solar wind plasma, the intensity and frequency characteristics of electromagnetic emissions change in ways that reveal information about the depth distribution of magnetic materials and the thermal response of surface layers to increasing charged particle bombardment. Radio observations detect bursts of enhanced electromagnetic emission that correlate with solar wind density fluctuations and magnetic field variations, indicating that the visitor's interaction with our star's extended atmosphere responds dynamically to changes in space weather conditions. These correlations provide insights into how interstellar objects behave during encounters with different types of stellar environments and magnetic field configurations throughout their galactic journeys. The interaction between 3I/Atlas and our solar system's magnetic environment thus creates a natural laboratory for studying plasma physics processes under conditions that combine the extreme environments of interstellar space with the specific characteristics of our Sun's extended magnetic field. Each measurement, each electromagnetic signature, each plasma wave detection adds to our understanding of how materials from distant stellar systems respond to the space weather conditions that characterize different stellar environments throughout the galaxy. The plasma phenomena generated during the visitor's solar encounter remain detectable long after its passage, as perturbations in the solar wind propagate outward through the solar system at the characteristic velocities of magnetohydrodynamic waves. These signatures provide a lasting record of the encounter that can be analyzed by spacecraft and ground-based instruments for months after the visitor has departed the inner solar system and resumed its journey into the galactic dark. Return to the Infinite begins as 3I/Atlas completes its gravitational embrace with our solar system and accelerates beyond the heliopause, carrying with it trace amounts of solar wind particles, cosmic dust, and electromagnetic signatures that will serve as evidence of its encounter with our star for billions of years to come. The visitor's trajectory bends around the Sun's gravitational field like light around a massive lens, gaining velocity and angular momentum that will propel it toward a distant rendezvous with stellar systems currently invisible to human telescopes, perhaps arriving at its next stellar encounter long after our own Sun has evolved beyond its current state. The mathematical precision of celestial mechanics ensures that every aspect of the visitor's future path can be calculated with extraordinary accuracy for the next several million years, until gravitational encounters with other stellar systems introduce chaotic elements that make long-term prediction impossible. Computer simulations trace the visitor's trajectory through the local galactic neighborhood, revealing that it will pass within several light-years of the red dwarf systems Wolf 359 and Gliese 623 before entering the gravitational sphere of influence of more distant stellar populations, where its ultimate fate becomes lost in the statistical uncertainty of galactic dynamics. As the visitor recedes beyond the orbit of Pluto, its surface temperature drops back toward the equilibrium values that characterized its interstellar journey. Approaching the cosmic microwave background temperature of 2.7 Kelvin that represents the baseline thermal environment of intergalactic space, the volatile materials that sublimated during its passage through the inner solar system freeze back into crystalline structures, preserving chemical and isotopic modifications that record its brief encounter with our star's radiation and magnetic environment. Advanced telescopic observations continue to track the visitor's position and brightness as it fades into the stellar background, each measurement adding precision to orbital calculations while documenting the gradual cessation of sublimation activity as solar heating becomes negligible compared to the visitor's internal thermal energy. The observational campaign will continue until 3I/Atlas becomes too faint for detection by even the most sensitive instruments, marking humanity's farewell to a wanderer that has shared its ancient secrets during a brief cosmic encounter. The visitor now carries within its structure trace amounts of solar system materials collected during its passage, microscopic grains of interplanetary dust, embedded solar wind ions, and chemical modifications produced by interaction with our sun's radiation environment. These signatures, invisible to current analytical techniques but potentially detectable by future civilizations with more advanced instrumentation, will serve as evidence that 3I/Atlas once visited a stellar system containing a small rocky planet where organic chemistry had evolved into technological intelligence. The mystery of the visitor's ultimate destination remains forever beyond human knowledge, as the chaotic nature of galactic dynamics prevents precise prediction of its trajectory beyond timescales of several million years. It may eventually be captured by the gravitational field of a stellar system with planetary bodies, where it could contribute its exotic chemistry to the formation of new worlds. Or it may continue wandering through interstellar space until the galaxy itself evolves beyond recognition. Theoretical calculations suggest that 3I/Atlas will spend the vast majority of its remaining existence in the cold vacuum between stars, where it will serve as a repository of chemical and isotopic information about multiple stellar systems encountered during its billion-year journey. The gradual accumulation of interstellar dust, cosmic ray processing, and occasional stellar encounters will continue to modify its composition in subtle ways that record the slowly changing galactic environment through which it travels. The visitor's departure marks the end of humanity's first comprehensive study of materials from another stellar system. Yet it also represents the beginning of a new era in astronomical research where such encounters will become routine as improved detection capabilities reveal the true population of interstellar wanderers that continuously traverse our galactic neighborhood. The techniques developed for analyzing 3I/Atlas will be refined and applied to future visitors, each adding to our understanding of planetary formation processes throughout the galaxy. Advanced space missions currently in the planning stages may eventually have the capability to intercept and study interstellar objects during their brief passages through our solar system, providing detailed in situ measurements that complement the remote observations possible with ground-based and space-based telescopes. These missions will require rapid response capabilities and autonomous navigation systems that can adapt to the uncertainties inherent in predicting the trajectories of objects discovered only weeks before their closest approach to the Sun. The long-term significance of 3I/Atlas extends beyond its immediate scientific value to encompass philosophical questions about humanity's place in a galaxy where materials and potentially even biological information circulate continuously between stellar systems over cosmic timescales. The visitor's presence in our skies demonstrates that we exist within a vast ecosystem of interconnected worlds where the boundaries between stellar systems prove more porous than previously imagined. The chemical and isotopic signatures measured in 3I/Atlas will be preserved in scientific databases and archives that may outlast the visitor's own existence, creating a permanent record of its composition and properties that future generations can use to refine their understanding of galactic evolution and planetary formation processes. Each spectrum, each measurement, each analysis contributes to humanity's growing knowledge of the cosmic environment that surrounds our solar system. As the visitor continues its journey toward the infinite darkness between stars, it carries with it the electromagnetic echoes of its encounter with human civilization, radio signals that briefly illuminated its surface, infrared radiation from our telescopes, and the faint gravitational perturbations created by our spacecraft and planetary motions. These signatures, undetectable by any conceivable technology, nevertheless represent humanity's contribution to the visitor's billion-year story. The return to infinite space restores 3I/Atlas to the cosmic silence that has characterized most of its existence, where it will resume its patient journey through the galaxy's vast emptiness, waiting for its next encounter with the light and warmth of stellar systems that may harbor worlds very different from our own. The visitor's brief passage through our solar system represents less than 1/10,000th of its total journey time. Yet these few months have provided humanity with unprecedented insights into the nature of materials and processes that operate throughout our galactic neighborhood. The cosmic irony persists as the visitor departs. An object that has traveled farther than any human artifact will reach for millennia continues its ancient trajectory with the same indifference to human attention that characterized its approach. It knows nothing of the scientific revolution it has inspired, the questions it has answered, or the new mysteries it has revealed about the galaxy beyond our solar system. The visitor fades now into stellar background radiation, its dark surface becoming indistinguishable from the countless point sources that populate the deep galaxy. The last measurements trickle in from telescopes straining to capture photons reflected from a surface growing ever more distant, ever more silent. 3I/Atlas settles back into the rhythm of cosmic time, where years pass like heartbeats and the motion of stars becomes the only measure of change. Beyond the heliopause, the visitor encounters the true interstellar medium once again. Hydrogen atoms scattered so thinly that cubic meters of space contain fewer particles than the best laboratory vacuums. Here, in the deep quiet between stellar systems, temperature approaches absolute zero and time moves according to the stately procession of galactic rotation. The visitor resumes its billion-year meditation, carrying within its crystalline structure the chemical memory of worlds that formed around distant suns. The observatory domes close for the night as Earth rotates away from the patch of sky where the visitor continues its journey. Computers process the final images, extracting every possible photon from sensors that have reached the limits of detection. The visitor's brightness has dropped below the threshold of human instruments, returning it to the cosmic anonymity it maintained for eons before its brief encounter with our solar system. In the expanding darkness, 3I/Atlas tumbles slowly end over end, its 8-hour rotation period keeping time with the cosmic silence. Its surface, warmed briefly by our sun's radiation, cools back toward equilibrium with the cosmic microwave background. Volatile materials that sublimated during its passage through the inner solar system condense once again into exotic ices that will remain frozen until its next stellar encounter, millions of years in the future. The visitor carries within its ancient structure the stories of stellar systems scattered across dozens of light years, chemical signatures of worlds that may no longer exist, isotopic ratios that preserve the nucleosynthetic history of stars that died before our own solar system formed. It drifts now toward constellations that will shift and change beyond recognition during its journey, toward stellar encounters that may redirect its path or capture it within new gravitational domains. The silence deepens as the visitor moves beyond the last traces of solar influence, beyond the scattered light of our star, beyond the reach of human observation. It joins the vast population of wandering worlds that migrate continuously through the galactic disk, carrying materials and information between stellar systems in a cosmic circulation that has operated throughout the Milky Way's history. The visitor sleeps now in the infinite cold, dreaming the deep dreams of geological time,